Now let's move on to performance optimization, some real-world improvements we implemented in production projects. GPU skinning optimization. In one project, we had a battle scene where each hero controlled a large number of minions. On screen, there were around 50 animated characters at the same time. We introduced Chenkehan's GPU skinning solution, a well-known GitHub project that's been around for years but is still extremely solid and practical. Before optimization, profiling showed animator.update, my 4.3 milliseconds. Mesh skinning, 5.8 milliseconds. That's nearly 10 milliseconds spent just on animation and skinning. Why so high? In a traditional app build, some of this work runs on worker threads or render threads, but in the minigame environment, multi-threading is not available. Everything runs on the main thread. That's why the cost is significantly higher. So we moved animation skinning and bone calculations to the GPU. After optimization, the total animation cost dropped from nearly 10 milliseconds to just over 2 milliseconds. That's a dramatic improvement. If your project includes many animated characters, such as SLG games, large-scale battles, or even fishing-style games, GPU skinning is absolutely worth considering. On minigame platforms, GPU capability is comparable to app environments. Offloading animation to the GPU is highly cost-effective. 2. URP optimization's volume update mode. In URP, there's a setting called volume update mode. If you're using post-processing volumes, the default setting is every frame. But in most projects, post-processing parameters, like bloom thresholds or color grading values, rarely change during gameplay. Updating them every frame is unnecessary overhead. Instead, switch the update mode to script. Then manually trigger updates only when needed, such as scene transitions, environment changes, specific gameplay events. This avoids redundant per-frame updates and reduces CPU overhead. Disabling unused LUT pass URP includes a default pass that bakes certain post-processing settings into a LUT texture. However, many projects don't actually use these features. If that's the case, you can safely comment out this pass to reduce rendering cost. One important note: if you modify this part of the pipeline, make sure to update related shaders accordingly. Otherwise, you may introduce color inconsistencies. Optimizing UI camera rendering, URP also includes some default rendering logic that may be unnecessary for specific cameras. For example, UI cameras typically do not render opaque objects, do not require dynamic lighting. So we added a conditional check in the scriptable renderer. If the current camera is a UI camera, skip operations like setup lights. These small optimizations add up and help reduce total render time. Heap memory optimizations. Now let's talk about some classic GC optimization cases. 1. Generic equality and boxing. In one project, we found heavy use of generic comparisons written like this: if value.equals, return. This is common, but it can cause boxing. Profiler showed about 28 bytes of allocation per call. When we switched to equality comparer T, default.equals, allocations dropped to 0. In high-frequency code paths, this kind of change can significantly reduce GC pressure. Number 2, avoid creating temporary objects in functions. Another common issue: creating temporary objects inside frequently called methods. Instead of instantiating new objects every time, promote them to member variables and reuse them. Call clear when needed. As long as capacity doesn't expand, you'll only pay the allocation cost once. This dramatically reduces GC spikes. 3. Array versus list in contains. We built a small demo comparing contains and list.contains. When profiling, using an array for contains caused GC allocations. Using a list for contains did not. So whenever possible, prefer list over array for containment checks to avoid unnecessary allocations. Final thoughts. All of these optimizations may seem small individually, but in minigame environments, where everything runs on the main thread, memory limits are strict, GC spikes are more noticeable, small inefficiencies compound quickly. Systematic optimization across animation, rendering, and heap allocation makes a real difference. That's everything I wanted to share today. Thank you.